All right, let's do this thing and name some stuffs and end on story time. Hopefully. There you go. Okay, so all right, so the first compound is the chiral center in that molecule. Is it R or is it S? Let's find out. I do believe you're right, but we'll work through it. Assign priority to everything first. So we know the oxygen has highest priority, then the hydrogen. Then we've got carbon and carbon were tied. Carbon and carbon were tied. Carbon versus this hydrogen on the end. So the longer chain gets higher priority. We connect the dots. It is in fact counterclockwise. So this is S. Right, so then for this one down here. Now remember, this came from the early class too. If I don't draw the hydrogen, it's still there, right? So the carbon with the nitrogen on it is still chiral because that fourth group, even though you don't see it, you know it's a hydrogen, right? You know it's there, even though it's not drawn in. So is this R or is it S? It's R, right? Nitrogen has high priority, hydrogen, low priority, right? And now I'm comparing carbon and carbon. And here's a spot where trying to break your tie as quickly as possible is kind of illustrated. I could work my way around the ring and I just keep getting ties over and over and over again. But if I hop off the ring and compare this hydrogen to this carbon, I've broken the tie immediately, right? I know that this is now 2 and this is 3. So 1, 2, 3. It's clockwise. It's R. I forgot to do my corny joke. I'll do it now for posterity. This is Snoop Dogg's favorite thing because he's like a 1, 2, a 3 into the 4. Okay, no one died. No one immediately hung up. So this is fine. This is fine. People are like, "Who's Snoop Dogg? And what is this rapping song you're talking about?" It's old Snoop Dogg. Before he was like Snoop Lion, this is like early Snoop Dogg. All right. So this is the easy way to do this, right? This is when the low priority group points away from you, right? So I told you before there are 3 sets of rules. There's low priority group away from you. I think we have that down. We can do that. Now, kind of rule 2 is low priority group on the wedge. Slash pointing at you. Right? I apparently left my model kits here last time, so we'll use them. Right? So, right, all the rules are, let's say the low priority group is the group that I'm holding. All the rules are made for low priority group pointing away from you. Right? When we have the low priority group pointing at you, we don't change the R or the S of that molecule. We're just changing which side of the molecule we're standing on, right? Clockwise and counterclockwise look backwards if you're facing the wrong side of the clock, right? If you're looking from a clock from behind, it looks backwards. But you have to realize, wait, clockwise didn't change, just where I'm standing, where I'm looking from changed, right? So when you have the lower part of the group on a wedge or pointing at you, I always say, do everything the same. Then switch at the end. All right. So I always end up saying this looks like it's R, but because the low priority group points at me, it is S. So you just do everything the same, and then at the end you check and go, is the low priority group pointing away from me or at me? And then that tells you if it's R or S. So if you have Again, we'll use our stock easy example here. One, two, three, four. We connect our dots. This looks like it is R, but the low priority group points at me, so I know it's S. Right, so you realize, hey, I'm on the wrong side of this molecule. I need to switch what I'm seeing. So this molecule has two chiral centers. We can assign both. We'll start with the chiral center that has the bromine, because that one's easy. Build some confidence. Right, low priority group points away from you. So this is just the simple base rules. You know bromine's 1, you know hydrogen is 4. And then methyl versus big ass chain. Big ass chain has priority. So 2, 3. And that is a technical term, big ass chain. Trust me. All right. So now we just connect the dots. 1, 2, 3. Low priority group points away from me. So this looks like it's R. Low priority group points away from me. It is R. We'll do the blue one. Again, we have hydrogen here. 1 and 4. Again, big chain versus methyl group. This one looks like it should be R, but the low priority group's pointing at us, so we know we have to say, oh no, this is actually S. So far, so good? All right. So the first thing you want to be able to answer is, how many chiral carbons are in this molecule? I will take a lower number than 4. 3. So the chiral carbons, I'll color code them. You've got the orange one, the green one, the blue one. So this carbon, we'll make it gray because gray is a sad color, right? That gray carbon right there is not chiral, right? Even though I put wedges and dashes on it, right? Those are two methyl groups. So they're the same thing. So, right, to be chiral, you have to be bonded to 4 unique groups. And since you're bonded to 2 hydrogens, it's not chiral. It's the same thing as like a CH2, right? Right here, this carbon's bonded to a hydrogen and a hydrogen. It's not chiral because it's bonded to 2 of the same group. It's bonded to 2 hydrogens. So being bonded to 2 methyls or 2 ethyls or 2 of the same whatever group, you can't be chiral. So this has 3 chiral centers in it. So we'll start with the orange one here. Oxygen and hydrogen, easy. 1 and 4. Methyl versus chain. We know chain wins. So this is going to be what? S. Indeed. Doodly. If we look at our green one now, what has highest priority? On our green carbon, what has highest priority? The alcohol. So the oxygen, that's 1. All right. What is our low priority group? There's no hydrogen. right? This is a methyl group, right? That's a methyl group. That's our low priority group, but it's a methyl because I don't have a hydrogen drawn on the end of it. So you remember when a line ends, it's just a methyl group. And then I guess is blue side or orange side, which side has higher priority? The blue side, right? Because you get to carbon and carbon, you're tied. Now we can immediately jump off the chain and get to hydrogen versus carbon. And so the blue side would win. So this will be 2, 3. So what is this? R, right? It looks S, but low priority group points at you, so it is R. All right. Now we'll do the blue one here at the end. Right, we'll draw our hydrogen in. So then we've got bromine is 1. Hydrogen is 4. Chain versus methyl group. So this will be right. It's going to look R, but be S because the low priority group points at us. Right. So the low priority group is what you're using to kind of verify if R is clockwise and S is counterclockwise for the way you're looking at this molecule. When the low priority group's away from you, R is clockwise, S is counterclockwise. When it's pointing at you, you have to switch it. And I just think it's easier to keep in your head R is clockwise, but now do I have to switch it here at the end? So you're not trying to switch back and forth. So just always R is clockwise. Now let me check to see if that's right or if I have to switch based on where the low priority group's pointing. So we have the easy one, low priority group pointing back. We have the slightly more difficult one where you have to say it looks like this, but it is this, right? It looks like the one, but it's the other. Then we have the third case, which is the hardest case, which is the low priority group is in plane. So it's not on a wedge or a dash. Right? So we can assign our priorities. 1, 2, 3, 4. And we see that our low priority group is in the plane. It's not a wedge or a dash. So our rules kind of break down, right? Because we have rules for when the low priority group is back. We have rules for when the low priority group is forward. But in plane's a little harder. Now there's 2 ways you can do this. Right? The first way I call mental Tetris, right? Where you're able to look at the molecule and say, okay, bromine's forward, chlorine's back, ethyl's down here, all right? And so I go 1, 2, 3. So that looks like it's S, but where I'm standing, the 4 group points at me, so it's R, right? That requires a lot of doing this kind of deal and making circles with your hands, right? And trying to see how the molecule looks in 3D. But there's a way you can do it kind of systematically where if you can't see the molecule in 3 dimensions, that you can do it every single time, but it just requires a little bit of work. And so the way you can do this more systematically is you redraw the molecule and you switch, or I'll just and switch, the 4 for the group on the dash. Right, so you redraw the molecule and you switch whatever 4 is for what's on the dash, and then you've given yourself the easy to do version of the chiral center. So we'll go right. So we redraw it. So the bottom one is the top molecule where we've switched the chlorine in this case in the methyl group. Whenever you switch two groups on a chiral center, you make these two groups are now enantiomers to one another. So the top molecule and the bottom molecule are enantiomers because you switched two groups on the chiral center. But what you did is you made a version of the molecule, you made the enantiomer that's easy to determine RNS for, right? So I can do the bottom 1, 2, 3, methyl is 4, this is S, right? And since they're enantiomers, you know if the bottom molecule is S, the molecule you're really interested in is R, right? So you just redraw it into the simple way to do RNS, and then you have to go like, okay, I determined the bottom structure, I determined the chiral center after I redrew it, and I know that the thing I started with was its enantiomer, right? So instead of having to like in your head turn the molecule and like figure out where everything is, you can always just switch the low priority group with whatever's back, make the enantiomer, and then assign it that way. So where this kind of falls down, and I can show you a trick here, is what happens when your molecule is really big, right? Or not even really big, like just moderately difficult to draw, right? So what if you have a situation where, you've got something like this, right? Like you don't want to have to redraw that whole molecule, right? Because it's a lot of work, right? And there's a lot that you could do and mess up. So all you really need to determine RNS is the priorities, right? So if you take this molecule and go, okay, bromine's 1, chlorine's 2, this chain is 3 because it has the branches closer, break the tie sooner. This group is 4. You can just draw a stripped down version of this chiral center. So not even drawing the whole molecule. You just need priorities. You just need 1, 2, 3, and 4, right? That's all you care about now, is you care where the priority numbers are. So now you can do the same thing. You're going to switch 2 and 4, right? You're going to redraw it, and you're going to switch group 2 and group 4. So when you redraw it, 1, 4, 2, 3. Right? Again, these are enantiomers. Right? So if the group I redrew, 1, 2, 3, this group is R. Right? That chiral center is R. So the one I started with is S. So I don't need to redraw that whole molecule. I can just draw like a simple stripped down representation of that chiral center and have that work as like a placeholder for all the different groups, because all you care about is the numbers. Once you assign the numbers, you don't need the groups anymore. You just need to work through the numbers and connect the dots. My one person in class just stepped out, so I'm just now in an empty room by myself. Just me and you, Zoom. You're right. You're my only human contact right now. All right. How many chiral carbons do I have in this molecule? 3. Right? So again, we've got blue carbon here. It's bonded to 4 different groups. Red carbon, green carbon. Right? Again, sad gray. This carbon, not chiral, because it has 2 ethyl groups on it. So let's work our way around. I'm doing a ring example because a lot of times people struggle with rings. So do a couple of those, make sure we're all on board. So for the nitrogen, are we R or are we S? All right, let us check. 1, 2, 3. Hydrogen points at us is 4. So this looks S, but the lower party group points at us. So R. All right. Everyone see that? Everyone on board with that being R? Okay. No one has said anything. Let's go to the other page of black boxes. There are no thumbs downs. Okay. We're doing it. Okay. Now, red carbon. Is that R or is it S? Bromine is 1. Methyl is 4. Carbon and carbon were tied. Carbon and carbon were tied. We could break this tie a whole bunch of ways. Oxygen has priority over nitrogen. Carbon has priority over hydrogen. So this green carbon has priority. So we're going to go 2, 3. 1, 2, 3. And this will be R. But one person came back. There are people again. Yeah, I'm not alone. There are both R thus far, yes. So then let's do the green dot. Is the green dot R or S? S. 1, 2, 3. Methyl group makes 4. It looks R, but because the low priority group points at me, it is S. So, do we feel relatively good about being able to assign R and S? So now we've got to use this to denote names, right? Now we've got to incorporate R's and S's into names so that when someone reads the name, they know which enantiomer of the molecule we're talking about. Let's go to our stock example. So when you're doing this, the first thing is just name it. Just get the correct name down and then worry about the stereochemistry, right? So what is the name of this? Yep, butane to all. So what you do when you name molecules with chiral centers is when there's only one chiral center, you just put the letter for R or S at the front of the name. So this will be 1, 2, 3. Hydrogen makes 4. So that's R. So this is R butane 2-ol. Yeah, make that this. So what is the name of that? So just, again, just name it. Don't worry about wedges and dashes. Just get me the right name first. Pentane 2. I will give you methyl. I will give you, you're close. How many methyl groups are on this molecule? So NN4 trimethyl, right? So there's a methyl group on the nitrogen. Well, there's 2 methyl groups on the nitrogen. And then there's a methyl group on the chain. You use N to denote those methyl groups are on the nitrogen. You use then the number to denote the methyl group on the chain. And now we've got the whole name. Now we have to figure out if it's R or S. So survey says nitrogen's high priority, chain, methyl group, hydrogen. This looks like it's S, but the low priority group points at me, so this is R again. It's RNN4 trimethyl pentane 2-amine. Not too bad? So that's when you have only one substituent, one chiral center on your molecule. What happens when you have 2 or more chiral centers? Step 1 stays the same, and that is name it properly. So step 1 is name this correctly. That seems what I would have put. I like it. So 4-ethyl, 5-methyl. Maybe there's actual dashes. Heptane 3-O. Everyone on board with the name? Okay. So now what we have to do is in front of the name, I'm not going to have enough space, I'm going to put it over it. You got to put parentheses, and then in order, list all the numbers that correspond to a chiral center. So it happens to be the numbers that correspond to where you have substituents, right? So in order, you're going to put 3, 4, 5, and then we have to, in front of for each number, assign R or S to that chiral center, and then put R or S with the number that corresponds to that chiral center. So this, right, this is number 3. So we're going to assign R or S to that. 1, 2, 3. Hydrogen is up, that's 4. So what is that? Is that R or S? it would be S, because it looks R, but the lower part of the group's pointing at me, so it's S. Right, then we have to do the green one, which is going to be number 4. Hydrogen's a gimme, right? Hydrogen's 4. So here, what has highest priority? The red side, the blue side, or the ethyl group? The red side, right? Because I compare carbon and carbon. All the way around I compare carbons, right? I'm like, carbon, 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 tied. Then I can compare carbon to oxygen. To carbon, oxygen's going to win. So that's going to give me priority number 1. Okay, I need to pick a different color, green. Priority number 1. And now I have this carbon and this carbon that I have to compare. Tied. Hop off the chain, compare hydrogen to carbon. Carbon wins. 2, ethyl group is 3. Or you could have just kept working down the ethyl chain and then you would have run out of carbons eventually. Right? So now we're going to go 1, 2, 3. And that is going to be it looks clockwise to me. Isn't it clockwise? And the lower part of the grip points away from me, so I think it should be R, right? It's on the dash, right? So remember, wedges are pointing out at me. Dashes are pointing into the board or into the screen away from you. So when I say like at me or away, it's, right, wedge is this, dash is this, right? So your wedge, dash. The best part is when I'm at home and I like put up the videos, I actually record myself doing the motions and stuff and then cut it into the video. It's really awkward, right? I had the blue dot is our last carbon, right? We know our hydrogen is going to be on a wedge pointing at us and be number 4. So then we've got methyl, ethyl, and big chain. Big chain wins. So big chain is our highest priority. Then ethyl, then methyl. 1, 2, 3. So this looks like it is S, but the low priority group points at me is on the wedge, so it is R. So far, so good. This seems semi-doable. No one on Zoom seems to be crying, so this is good. My one person in class hasn't left again, so like we're doing all right. Do we need to do another one real quick? Do one more, and then we'll do story time. Educational story time. Step 1, let's name this. Is bromochlorodimethyl cyclohexanol. And we know we're going to start numbering at the OH, right? The carbon that has the alcohol, since it's the only thing that gives us the suffix, it has to be 1. So we're going to have 3, 3, 5, 5 dimethyl cyclohexanol. And either way I numbered, I got the same numbers, right? I got 3, 3, 5, 5 either way. Bromine comes first, so bromine gets the lowest number. How many chiral centers do I have? 2. So I need to have 2 numbers with 2 letters in front of them, right? So I need something like, is going to be 1 and 3, right? Because the carbon with the OH is chiral. So this is going to be, we'll pick a different color here. 2, 3, hydrogen is 4, right? So the OH is 1, carbon and carbon is tied, carbon and carbon is tied. I can go like bromine versus carbon, bromine wins. So that whole lower chain is 2, then the other chain is 3. So that is going to be what? R. So the chiral center down here with the bromine and the chlorine, this one's going to be a little tricky. 1, 2, 3, 4. Because I have carbon and carbon tied, and then I can compare OH to carbon, and the OH wins. So now we have our low priority group in plane, and it'd be really hard to redraw the whole ring, right? And move stuff around. So this is where that trick where you just use the stripped down chiral center works. So you can go 4, 3, 1, 2, and then redraw it to be 2, 3, 1, and 4. So this is R, which means the thing I started with, all the way over here, is S. So this is 1R, 3S, 3 bromo, 3 chloro, 5,5-dimethyl, cyclohexane, O. Story time. And story time starts with a very simple question. Why do you care? Why does stereochemistry matter at all? Right? And so I'm going to take an example from Dirty Dirty Biology. Let me share the slide for you guys. Right? Zoom should be getting a big slide now. One big slide. Right. So this is thalidomide. And in the 50s and 60s, it was widely used in Europe as an effective treatment for morning sickness. Right? The compound exists as a racemic mixture, R and S. And racemic just means it's a 1-to-1 mixture of enantiomers. So it's 50% R and 50% S. We have the little squiggly line here. That little squiggly line just indicates that it's a mixture, right? That it's half wedge, half dash, squiggly, right? So this was used, like I said, extensively in Europe. And the reason this matters is this compound caused horrible birth defects. So one enantiomer, the S enantiomer, fits into the major group of DNA and inhibits the expression of growth factors that cause limb buds to form. Basically, it prevented fetuses from developing arms. And then the R enantiomer was sleep-inducing and prevented feelings of nausea. So one enantiomer was good, one enantiomer was bad, right? Enantiomers have the same physical properties. They act exactly the same unless they're around other things that are chiral. So the example I use is like your shoes are enantiomers, right? After a hard night of drinking, I know none of you'd ever do that, right? If you wake up and the lights start and you grab your shoe, you might not realize if you have the right shoe or your left shoe. But then if you put it on the wrong foot, you're like, something doesn't feel right. But your shoes are the same weight and they kind of look the same. But like if you go to put it on the wrong foot, it's gonna feel wrong, right? It's gonna be like, oh, these don't match, right? So chiral molecules have all the same properties, but when you get into the body, everything in your body is chiral. So one enantiomer is going to act differently than the other. Right? The reason this didn't happen here is Fake a Nerd, Frances Oldman Kelsey at the FDA was reviewing the approval for this drug. And she was the first one to put together that, oh my gosh, Europe has this really high rate of birth defects, way higher than anywhere else in the world. What are they doing differently than the rest of the world's doing? And that was they were taking thalidomide. So she's the one who put the stop on thalidomide coming here. So the effect was you had bunches of children all through Europe that they basically their arms didn't develop. They got like hands, but kind of no upper arm because the S enantiomer bound to the DNA and said, hey, don't form the arms. So, like 5 years ago now, the company that made thalidomide, that still exists, paid out like multiple millions of dollars to survivors who were harmed by thalidomide back in the 50s and 60s. And so, because of thalidomide, now whenever we make a drug, we have to do one of two things. We either have to make only the single enantiomer, right? We have to make the R enantiomer or the S enantiomer. We're not allowed to make both, right? So we have to say like, okay, I know the S enantiomer is good. I'm going to make the S enantiomer and test it, but I'm never going to make the R enantiomer and put that in the pill because I don't know what the R enantiomer does. The other thing you can do is you can make that racemic mixture, the one-to-one mixture, because it's way easier, right? It's hard to make things that are chiral in one enantiomer. It's easy to make mixtures. But what you have to do is you have to test both enantiomers and prove that, hey, my S enantiomer is my medicine. It does something. The R enantiomer doesn't do anything, but is also not harmful. So if I make both of them, I'm going to give medicine and garbage, and the garbage doesn't hurt them. So now we take into account the enantiomers of every drug we make to make sure that we aren't ever making a harmful enantiomer that can injure patients. Now, if you're like, I don't care about arms, right? I'm all about getting that paper. Fine. Story about how enantiomers can make you rich. There's a chemical company, a pharmaceutical company called Albany Molecular, and it was started because Merck, the giant pharmaceutical company, made a mistake in a patent. So when we patent drugs now, we will patent the R enantiomer and we'll patent the S enantiomer. And you're also supposed to remember to patent the mixture. Well, Merck, they made a new drug. They patented the R enantiomer and the S enantiomer. The R enantiomer was, let's say, that was the good one, that was the medicine. And the S enantiomer didn't do anything, but it wasn't harmful. So these two chemists that worked for Albany Molecular saw the patent and went, or worked for Merck, went, oh man, they didn't patent the mixture. So then they patented the mixture and started a company where they sold a generic version of Merck's brand new drug as a mixture of isomers because the one isomer wasn't bad for anyone. So they were able to develop and bring to market a drug and do none of the actual work for it. They had to do none of the R&D, but because they understood how patents work and, enantiomers, they could patent one drug. And this company's been around for like 20 or 30 years now based off of a mistake. And these dudes have made millions of dollars. So, with that, I think we're good. We'll do optical rotations and stuff on, I don't know what today is, on Monday.